All right, so what I'm going to be discussing today is I'm going to show how steps minimize dissipation in rapidly driven stochastic systems. And this is going to apply in general, but I want you to keep in mind this model system that I have shown here, which is that of a breathing harmonic trap. So we start from some initial control parameter value, that's say the confined state of this harmonic potential, and our goal is to go to some final control parameter value, which is going to be, in this example, the open state. And what we're going to be looking at is how to optimally drive between these two control parameter values. And we're going to specifically look at the fast limit. And what we're going to find is that in general, the optimal protocol in the fast limit is always going to start from its initial value, jump to some optimal step value, sit there for the entire duration, and then jump at the end. And this holds quite generally for a wide class of different systems. Okay, so to lay a bit of the groundwork, the type of control that I'm going to be discussing today is called parametric control. And we're going to imagine we go from some initial control parameter to some final control parameter in some generalized control parameter space. Here is just a rectangle. And you can imagine that the different paths that you take through control parameter space to get from one to the other are going to differ in their energetic cost. And we're looking for the path that has the minimum energetic cost. Specifically, we want to minimize the work done. So here we use the standard definition of work where F, this lowercase f here, is the force conjugate to the control parameter. And the control parameter we denote as lambda of t. Then here lambda dot is just the control parameter velocity. U here is the internal energy. And then we have these angle brackets with a subscript capital lambda. That's just going to denote a non-equilibrium average. Now, in this average work, the only unknown is this non-equilibrium average force. However, this is quite a tricky quantity to optimize. And specifically, it depends on the entire protocol history. It is generally a nonlinear function of this control parameter protocol. And if you're doing like overdamped dynamics, for example, typically like each time you want to test a new trajectory, you're going to have to solve the Fokker-Planck equation. So this means that general solutions are mostly intractable except for a few simple systems. So rather than trying to solve it in general, we're going to look at approximate methods. And specifically, we know that in the slow limit, the optimal protocols have been known for like 10 years, and we have general methods for finding these. But what I'm going to be discussing today is the opposite limit, looking at specifically a very fast protocol. So what we have shown is that when you're going very fast, it's not really the work that's the important quantity, but it's more useful to think about the saved work. And what this is how much work you save in comparison to an instantaneous protocol. So you can imagine with this harmonic trap, you start at your initial stiffness, and then you just infinitely fast jump to the end of your protocol. And that's what this instantaneous work quantifies. So you want to quantify how much work do you save in comparison to that by spending a short amount of time relaxing towards equilibrium. Now, it turns out if you go very fast, you can get a very simple approximation for this saved work in terms of this first term here, which is we call the initial force relaxation rate. And what this R quantifies is the relaxation rate of the initial mean conjugate force at the current control parameter value. So this little subscript lambda I here just signifies that this quantity is averaged over your initial distribution. However, it doesn't only depend on your initial control parameter value, because as you change your control parameter, your distribution remains largely close to where it started. However, how quickly you relax towards your new equilibrium changes depending on where you change your control parameter to. Okay, and then the second term in the saved work is just sort of the distance you have remaining to travel. So this final control parameter value minus your current control parameter value. And what's really nice about this form for the saved work, which we want to, in this case, maximize, is that it doesn't depend on your control parameter velocity or the history of your protocol. And what this means is that to optimize this quantity, it's almost trivial because it just depends on your current control parameter value. So when you can do this optimization, you find a single maxima. And what this implies is that the minimum work protocol has a jump to and from what we call the step or the short time efficient protocol value at the beginning and end of the protocol. So basically you start at your initial value, you jump to this one that has sort of this maximum trade-off between your relaxation rate and distance remaining, and then you sit there for an entire duration before jumping at the end. And then just mathematically, this is what the optimization corresponds to. This is just maximizing the argument up here. And then if you do this type of protocol, this is how much work you're going to save. Now, this is a bit more instructive if we, instead of just looking at some equations, look at a plot. So I really like this kind of plot that I'm showing here, which is a force versus control parameter diagram, which is really nice because when you plot things in this way, then work is given by the area under the curve on this type of plot. So here we're looking at the breathing harmonic trap going from here, this is the open state to a tightly confined state. Now, if you do this infinitely slowly, the work that you do in going forwards and backwards is going to be the same, and it's going to be given by the free energy difference. Now, in the opposite limit of a very fast protocol, the work that you do, you start at your initial conjugate force, you jump all the way to the end, and then at the end, after your protocol, so not during the protocol, we assume you can relax to equilibrium so we can complete the cycle. Then the heat that you dissipate or the work that you've done is given by this relative entropy between your initial equilibrium distribution and your final equilibrium distribution. So that's the area between this red dotted line and this dashed line. Okay, and then you can do the same process in reverse. So what we're looking at is a very short protocol. So rather than going infinitely fast, we have some short amount of time, delta t, to relax. So the optimal process to do this is given by this step, where instead of jumping to the end, you jump to some intermediate optimal value. You sit there for the entire duration, relaxing towards equilibrium, which means you move down towards this dashed line here, and then you jump at the end when you run out of time. And essentially the width of this rectangle is given by this distance here. And then the height is given by how far you have relaxed towards equilibrium, which is this relaxation rate times the protocol duration. And essentially what this optimization does is basically we're just maximizing the size of this rectangle. So in doing so, we have maximized the saved work and found the optimal protocol in the fast limit. Okay, and then you can do this all in reverse, and the amount of work that you save is going to be different when you go backwards. But essentially the process is the same. Now, this doesn't just hold for this model system or breathing harmonic trap, it holds in general. And now that we've found the optimal protocol, a first important question to see is how well does this actually perform? Now, one thing that I'd mentioned before is that we've known for quite a while how to compute the optimal slow protocols. So we can compare it to that, as well as we're going to compare it to the optimal, we're going to compare it to what we call a naive protocol. So the naive protocol corresponds to just linearly driving it between the two endpoints. So linearly driving the stiffness in this case between the open state and the closed state. So here we can look at the naive work minus the designed work, which basically if this quantity is positive, then we're doing better than this naive protocol. So that's sort of the benchmark. So I just have, And then on the horizontal axis here, we have the protocol duration. So basically the right side here corresponds to long duration, that's a slow protocol, and the left side will correspond to short duration, that's a fast protocol. So first of all, we have what we've known before, which is the slow optimal protocol, given by this dashed blue curve. And we see that this performs better than the naive, provided your duration is sufficiently long. And then what I've talked about today, that step, that's this fast optimal here. If your duration is relatively short, then this does quite well, much better than the naive. And then what we do, and what is really powerful about what we've found here, is that we can take this slow optimal and this fast optimal by just adding jumps to the beginning and end of the slow optimal protocol that get bigger and bigger as you go faster and faster. We can compute what we call an interpolated protocol, which looks something like this. So what we can see is that because we have both these two limits, we can interpolate between the two and create a protocol that does well at all speeds. And then just for comparison, here's the exact optimal, because for this specific system, you can compute the exact optimal protocol, and it does pretty well compared to the interpolated does pretty well compared to even the exact optimal solution in this case. And the really nice thing about this is that these solutions in the slow limit and the fast limit in particular are way easier to calculate than this exact optimal system, and it apply way more generally.
You have 1 minute left.
Thank you. And then to conclude, I just wanted to give a bit of like a more general perspective on this type of parametric control. So here I have a little diagram that's sort of inspired by this paper by Banaka and Defner, where they showed a similar type of diagram where we have on the horizontal axis the driving speed, and on the vertical axis the strength of driving. So here we have the slow limit, the fast limit, the weak limit, and the strong limit. I'm going to look at in what cases do we know the optimal solutions. So generally the general solutions are intractable for most systems, but we know the solutions for slow driving and weak driving, and both of these are sort of governed by linear response, and these have been known for quite a while. And then what we've discussed here, we sort of fill in this other side of this rectangle with these short time efficient protocols with the fast driving. And that means that you can get these interpolated protocols that go between the two. And then you can do this not just for one-dimensional control, but you can do this for multi-dimensional control, which we do in this article here. And then just a little bit more of an advertisement. We've recently been looking at optimal control in sort of this strong limit to we sort of partially filled in this top limit here, which basically if you have strong harmonic trafficking potentials, we can find the optimal protocols as well. So this is just to give like a more general perspective that we have now a much more clear picture of how to do this type of parametric control. And with that, I would like to thank you for your attention, and I welcome any questions.